kita masuk di pencuplikan sinyal waktu kontinu. Ya. Dari judulnya kita lihat proses itu apa? Bagaimana kita mengubah sinyal kontinu melalui antarmuka analog to digital, kemudian kita dapat sinyal dalam waktu diskrit, kemudian kita pengolahan sinyal, kita dapat outputnya, dan untuk dikembalikan lagi kita menggunakan konversi dari digital to analog. Kurang lebih inilah materi hari ini. Ruang lingkupnya, pencuplikan periodik, representasi pencuplikan di kawasan frekuensi, rekonstruksi, pengolahan, perubahan rate pencuplikan, dan pengolahan sinyal secara digital ke analog. Nah, yang perlu diperhatikan fenomena aliasing. Ya. Cuplikan periodik, kenapa disebut periodik? Karena ada fungsi sampling, ya, fungsi sampling yang dialirkan secara periodik, ya, yang dialirkan secara periodik, sehingga sinyal kontinu, input sinyal kontinu, ya, kita lewatkan ke proses sampling, kemudian didigitalisasi, kita dapat XN, sinyal waktu diskrit, dengan mengambil T-nya sama dengan NT, N integer, ya. T-nya NT. Nah, T-nya periode pencuplikan. Periode pencuplikan. Pencuplikan secara periodik itu ada sinyal sampling ST yang periodik, ya, periodik yang muncul setiap T untuk mencuplik sinyal kontinu amplitudonya, ya. Kemudian didapatlah sinyal tercupliknya, ya, sinyal tercupliknya, tapi masih dalam bentuk T, ya. Nah, persamaan matematis yang mendukungnya, tadi sinyal periodik dari fungsi sampling tadi adalah suatu deretan impuls yang periodik sejauh NT, ya. Sejauh NT. Prosesnya adalah perkalian, ya, perkalian. Jadi sinyal kontinu T dicuplik atau dikalikan dengan sinyal sampling, ya. Maka kita dapat XN sama dengan XCNT, ya. Kalau dilihat dari spektrum frekuensinya melalui transformasi kuliah waktu kontinu, ya, maka perkalian di domain waktu sinyal kontinu dengan sampling perkalian, ya, modulasi perkalian, maka di daerah frekuensi itu adalah konvolusi, ya. Konvolusi itu artinya dia akan tergeser di domain frekuensi setiap periode sampling, ya. Jadi setiap periode sampling dia akan muncul kembali ya, spektrumnya. Nah, maka perlu diperhatikan di sini supaya tidak terjadi aliasing, maka frekuensi sampling harus lebih besar dari 2 kali frekuensi Nyquist yang disampling. Ya. Kalau dia lebih kecil, maka akan terjadi aliasing. Ya. Di sini akan ada tumpang tindih. Ya. Merekonstruksi ya tentu kita memfilter. Kalau kita lihat spektrumnya tadi, dia berulang setiap frekuensi sampling, ya, berulang setiap frekuensi sampling. Maka kalau ditangkap dengan low pass, maka tinggal satu, ya, tinggal ditangkap dengan low pass, kemudian ini direkonstruksi untuk mendapatkan kembali sinyal kontinyunya. Ya, itu mendapatkan kembali sinyal kontinyunya. Ya, kita masuk teorema pencuplikan Nyquist. Ya. XJT adalah sinyal dengan frekuensi omega n disebut frekuensi Nyquist. Frekuensi 2 omega n disebut rate Nyquist. Ya. Di sini ada omega kecil, ada omega besar, omega kecil pangkat J omega, omega kecil, itu adalah frekuensi digital. J omega, frekuensi analog. Hubungan antara omega kecil dengan omega besar adalah omega kecil ini omega besar dikalikan T. Ya. Kalau dalam Hertz dia F kecil hubungannya dengan F besar T. Ya. Di domain frekuensi, teorema pencuplikan Nyquist kalau kita lihat yang tercuplik kita lihat contoh. Ada sinyal kontinyu fungsi kosinus 4000 Vt. Ya. Berarti 2V Ft, berarti frekuensinya itu berapa? Ya, 4000 Vt, dicuplik dengan periode pencuplikan 1/6000. Ya, 6000 Hz. Maka Xn-nya menggantikan T dengan Nt. Ya, T dengan Nt, T-nya 1/6000. Ya, kita dapatlah kosinus omega 0n, ya, 2pi per 3 omega 0-nya kali n. Ya, 4000 per 6000, 2 per 3 V per n. Ya. Dalam frekuensi digital, kosinus omega 0n, frekuensi naturalnya 2pi/3. Frekuensi sampling tadi 2pi/t, 12.000 V, omega 0-nya 4.000 V, ya, omega 0 yang besar, omega besar, 0 dengan omega kecil, yang tadi adalah perkalian dengan T. Ya. 2pi/3 kalikan 6.000 menjadi 4.000 V. Ya. Jadi secara tidak langsung, omega digital adalah omega analog dikalikan dengan T. Frekuensi hertz digital F kecil sama dengan frekuensi analog dikali T. Ya. Syarat Nyquist harus 2 kali frekuensi Nyquist. Jika T-nya frekuensi pencuplikan 1500 Hz, T-nya 1/1500, apa yang terjadi? Maka omega 0-nya 4000 dibagi 1500 kali Vn. Ya, kosinus omega 0. Omega 0-nya 8pi/3. Ya. 4 kali 2pi/3. Ya. Syarat Nyquist-nya tidak dipenuhi. Ya, 1500 syarat Nyquist-nya tidak dipenuhi.
Well, in this lecture, we're going to look at aliasing and the sampling theorem using a simpler approach than is usually done. And we're not going to rely on extensive use of Fourier transform properties and identities, but rather on a simple mapping between continuous and discrete time frequency. So there's 3 key facts that are going to play out in this discussion. The first one is that an arbitrary signal can be expressed as a sum of sinusoids. And that's basically the Fourier transform. So if we look at how sampling and aliasing affects sinusoids, we can piece together how this is going to affect arbitrary signals because it's just going to be a superposition. The second fact is that when we sample a continuous time sinusoid at intervals of t seconds, we get a relationship between continuous time frequency uppercase omega and discrete time frequency lowercase omega. Discrete time frequency lowercase omega is units of radians. It's going to be equal to continuous time frequency uppercase omega times the sampling interval cap t. So if I take a complex sinusoid, e to the j omega t, I sample it at intervals of n times capital T seconds, then I get e to the j omega t times n. And I can view this as corresponding to a discrete time sinusoid, e to the j lowercase omega times n. And right away you see again that lowercase omega is equal to uppercase omega times t. Now the third fact is the fact that discrete time sinusoids are only unique over a 2 pi interval of frequency. You can easily show that if I take a sinusoid e to the j omega n and I shift the frequency by any integer multiple of 2 pi, that I get exactly the original sinusoid back. And so we have e to the j omega n times e to the j 2 pi L times n, and e to the j any integer multiple of 2 pi is exactly equal to 1. So this is e to the j omega n. And this means that we can't distinguish between a sinusoid with frequency omega and a sinusoid with frequency omega plus 2 pi or omega plus 8 pi. Any integer multiple of 2 pi is going to give us exactly the same sinusoid. So first of all, let's use the second fact that we have this relationship between discrete time frequency lowercase omega and continuous time frequency uppercase omega. We can plot discrete time frequency as a function of continuous time frequency, and we just get a straight line, and the slope of this line is capital T. Now the fact that discrete time sinusoids are only distinct on a 2 pi interval of omega means that we can restrict the range that we wish to consider for the discrete time sinusoid. So it's conventional in signal processing to use the range minus pi to pi, and I've indicated that on the graph here by the dashed blue line. So it would be, say, this interval here is the interval minus pi to pi, and that's an interval over which the discrete time sinusoids are unique. Now they'd also be unique over this interval from pi to 3 pi or from minus pi to minus 3 pi. So when I do that, the frequencies on omega that were associated with the interval between pi over t and 3 pi over t, which correspond to lowercase omega, discrete time frequency in this interval between pi and 3 pi, those wrap back around to the interval I'm going to limit myself to, right? Because I can shift any frequency in this interval, I can subtract 2 pi, and I end up with a frequency in the interval minus pi to pi. So my function now takes the form that's shown down here in the bottom. So for example, if I have 0.5 pi over t, say I have a sinusoid here, and I map that up to the corresponding discrete time sinusoid, I see it's going to be pi over 2. However, if I also have continuous time sinusoid with frequency 2.5 pi over t, that's right here, I see that I end up in the exact same location, again with omega equals pi over 2. So this tells us the relationship between continuous time frequency uppercase omega and discrete time frequency lowercase omega. So there's two important aspects of this representation or relationship between these two frequencies. First of all, continuous time sinusoids, if the magnitude of their frequency is outside of this interval, because of this wrapping that we had where the part between pi and 3 pi wraps down to become minus pi to pi, continuous time sinusoids outside of this interval end up appearing at the incorrect discrete time frequencies, omega. We saw that we had 2.5 pi over t, and that sinusoid showed up at pi over 5 radians for discrete time frequency. It's called aliasing because the sinusoid shows up at a different frequency than you would expect. Now the second observation from this relationship between continuous and discrete time frequency is that if I want to go the other way, in other words, start with a discrete time sinusoid and figure out which continuous time sinusoid corresponds to that, I have some ambiguity. Because if I tell you that my discrete time sinusoid has frequency pi over 2, you don't know whether the continuous time sinusoid is pi over 2t, or 2.5 pi over 2t, or it could be minus 1.5 pi over t. So given the frequency of the discrete time sinusoid, one cannot uniquely determine the continuous time sinusoid frequency unless we know something about the range of possible continuous time sinusoidal frequencies. And it's pretty typical to assume that we're going to be only considering this region between minus pi over t and pi over t, and if we limit our continuous time sinusoids to that interval, then there's a one-to-one relationship between discrete time frequency and continuous time frequency. And we can invert this function. In other words, if I have a discrete time sinusoid, I know what that should correspond to in terms of a continuous time sinusoid. We can state this condition about recovering the continuous time frequency from the discrete time frequency in something known as the sampling theorem. That applies more generally to a signal x of t, which has a Fourier transform x of omega. So we're talking about a range of possible sinusoidal frequencies in x here. And if that signal is band limited, in other words, the Fourier transform is 0 for frequencies greater than some number w radians per second, then in order to have a unique relationship between the signal x of t and its samples x of nt, we must have that w be less than pi over t. In other words, all the frequency content of the signal must lie in this interval. Given the frequencies in discrete time, because we've sampled the signal, from that frequency content we want to convert it to a continuous time signal. And that only happens uniquely if we're in this interval. So the sampling theorem basically tells us how big t needs to be for a particular bandwidth of a signal. T must be less than pi divided by the bandwidth of the signal in order for us to be able to uniquely take the samples of the signal and figure out what the original continuous time signal was. Now there are a couple definitions that we're going to introduce here. 2 pi over t is known as the sampling frequency, and that's in units of radians per second. It would be 1 over t in units of hertz. Then w, the bandwidth of the signal, is also sometimes called the Nyquist frequency, whereas 2w is called the Nyquist rate, because that's the minimum sampling rate. We need to sample at least twice the highest frequency present in the signal to be able to reconstruct the continuous time signal from the samples, to have that unique relationship. Now it's useful to look at what is the Fourier transform of the sampled signal. Now usually the Fourier transform is applied to continuous time signals, and we're talking about applying it to a sampled signal. And the way that works is as sketched out here. We have some signal, x of t is a Fourier transform x of omega. If we sample that at intervals of n times t, then we get samples x of nt, which we'll call x of n, and x of n is a discrete time signal, so that should have a discrete time Fourier transform x of e to the j omega. Well, the way we're going to define the Fourier transform of x of n is based on the discrete time Fourier transform. We're going to take x of e to the j omega, and we're going to use our relationship between discrete time frequency and continuous time frequency so that we can define a Fourier transform of our sampled signal, we'll call that x of s of omega, as the discrete time Fourier transform with discrete time frequency omega replaced by continuous time frequency uppercase omega times the sampling interval. So all we're doing is scaling the frequency variable, and we're going to call that our Fourier transform. We know, of course, that the discrete time Fourier transform is 2 pi periodic. If you shift omega by 2 pi, you get exactly the same values of the function, and therefore our Fourier transform xs of omega is going to be 2 pi over t, which will use the notation omega sub s for 2 pi over t. That'll be the period of xs of omega. Now I've resketched our relationship between continuous time frequency and discrete time frequency here, but I've added another set of labels on the discrete time frequency axis, and that's through this mapping that we're using to get the Fourier transform. So we have some signal x of omega that we're sampling, and in general it has some Fourier transform that I've drawn here, and we're going to try to figure out how does this go through sampling and end up giving us the Fourier transform of the sampled signal. Well, the frequency content that is in this region here near 0 on the horizontal axis maps through this function to something on the vertical axis. And this happens for all of these different sections of this signal that we're sampling. You can sketch this out. If I look at this section over here, it gets mapped up through this branch of the relationship between continuous and discrete time frequency. So it generates a term that looks like this. So here frequency axis is vertical now. So this section here labeled -2 gives me this component as showing up in the low frequency regime, okay, because -2 omega sub s aliases to 0. And then this second branch here labeled -1 maps the frequency content of my signal that was between minus omega s over 2 and minus 3 omega s over 2 into this interval between minus pi and pi. So I've got this term here corresponding to this going through this branch, the minus 1 branch. And then the one at 0 goes through this branch at 0 and comes out here, and so on. At 1, we have what's centered on omega s maps back to being centered on 0. What's centered on 2 omega sub s also gets centered on 0. And these things all add up. Okay, so all of these frequencies alias, frequency content in all these different regions alias down into the low frequency regime, and the net result is we get the sum of all of these. This section here is actually a shifted version of the original signal. I can shift this to 0 by moving this whole signal to the right by 2 omega sub s. I can shift this version to be centered on 0 by moving this entire thing to the right by omega sub s. This one is already at 0, then this one I need to move the signal to the left by omega sub s, and to get this one centered on 0, I move it to the left by 2 omega sub s. So it's the superposition of all these terms that have alias down into this band between minus pi and pi for lowercase omega that we're going to add up. The expression becomes the Fourier transform of the sample signal is equal to 1 over t, where that's the sampling interval, and that's a constant that's needed to preserve the energy appropriately. The sum from k equals minus infinity to infinity of the shifted versions of my original signal that I'm sampling. And they're shifted by integer multiples of omega sub s, the sampling interval, which is just 2 pi over t. So let's do an example now where we look at the sampling theorem and this expression that we derived for the Fourier transform of the sampled signal. We're going to assume that the signal we're going to be sampling has Fourier transform as shown in this sketch, and this particular signal is band limited to 10 pi radians per second because the Fourier transform is 0 for values of omega less than minus 10 pi and for values of omega greater than 10 pi. Bandwidth of this signal is W equals 10 pi radians per second, and hence the sampling theorem says that we need pi over t to be greater than the bandwidth, and that tells us that the sampling interval, to avoid aliasing and uniquely reconstruct this signal, needs to be less than 0.01 seconds. So in the first example, we'll assume that this condition is satisfied by choosing a sampling interval to be 0.05. This gives us a sampling frequency, 2 pi over t, of 40 pi. So here's what xs of omega looks like in this case. I've got 20 for the amplitude because here it was 1, and 1 over 0.05 is 20. So I've scaled things by 20. My k equals 0 term in this summation has no shift whatsoever, so this is just the original spectrum of the signal going from minus 10 pi to 10 pi. Then when I have k equals 1, I'm shifting this Fourier transform to the right by 40 pi, so it's located here as labeled. Then when I have k equals 2, I'm shifting it to the right by 2 times 40 pi or 80 pi, and so on, this process. Then on the other side, when we have k negative, it's shifting this Fourier transform to the left by 40 pi and by minus 80 pi, and so on. All of these individual replicates of the original signal are well spaced apart and distinguishable. We can sketch the discrete time Fourier transform as shown down here. And this relationship says that 2 pi over t always maps to 2 pi. So what was at 40 pi, which is 2 pi over t, now maps to 2 pi. And we have basically the 2 pi periodicity of the discrete time Fourier transform that we expected. And so in the second example, we're going to choose a sampling interval that violates the conditions of the sampling theorem, because choosing t equals 1/8 is greater than 0.1 second, which was required by the sampling theorem. So we're going to expect to have a problem with uniqueness of reconstruction here. Well, in this case, 2 pi over t, the sampling frequency, is 16 pi. So when we apply our expression for the Fourier transform of the sampled signal, we're going to take, as I've shown here with the dashed lines now, because these are overlapping, we're going to take our original signal spectrum, that gets located centered on the origin, and that's my k equals 0 term. And then the amplitude is scaled, of course, by 1 over the sampling interval, so that's 8. Then we're going to shift this by 16 pi for k equals 1 and replicate that Fourier transform. And then we're going to add that to what we had for k equals 0. And similarly, we're going to shift for k equals 2, for k equals minus 1, for k equals minus 2, and so on for k going from minus infinity to infinity. Now, I've shown the individual shifted replicates, and what this expression says is that we're going to add those up. Well, when we add those up in this region where they are overlapping, we get, I've shown it in the dark blue here, is that where they overlap, the downward sloping line and the upward sloping line sum to give us actually a constant. So we can no longer identify the Fourier transform of the original signal here. And we've got a sum of two things, and there's no way to pull that apart without knowing what the original Fourier transform was. In other words, we've lost uniqueness. Okay, so I've got a case where the sampling theorem is violated and we can't uniquely identify the Fourier transform of the original signal. Again, we can scale the Fourier transform axis, capital omega, into the discrete time Fourier transform axis, lowercase omega, because of the way we defined xs of omega to simply be the discrete time Fourier transform evaluated when omega was equal to uppercase omega times t, and we get the discrete time Fourier transform shown down below. And again, omega sub s, which in this case was 16 pi, is 2 pi over t, and that always maps to 2 pi.
Oke, rekonstruksi itu adalah bagaimana mengubah dari sinyal diskrit menjadi sinyal kontinyu. Ya. Rekonstruksi, sampling, konvolusi dengan filter HR, ya, proses pemfilteran tadi, maka dia adalah menjadi interpolasi dari suatu fungsi. Kalau kita lihat, interpolasi dari nilai-nilai xn yang dijumlahkan diinterpolasi, ya, interpolasi dari suatu fungsi sinus x per x, ya, sin x per x, amplitudenya dijumlahkan. Nah, secara matematis rekonstruksi, ya, adalah nilainya dengan sin x per x dijumlahkan. Ya, baik error di pengolahan sinyal waktu. N direkonstruksi, ya. Di sini xj omega dsn, yj omega, yr adalah yn dikalikan dengan fungsi sampling. Blok lengkapnya, bagaimana mengolah sinyal kontinu AD ke DA, Sinyal kontinu kita butuh filter anti-aliasing untuk membatasi bandwidth, ya. Kemudian dilewatkan suatu rangkaian sample and hold, ya. Di sampel, dicuplik, ditahan nilainya, kemudian kita memiliki nilai kontinunya, ya. Kemudian dilewatkan konverter, analog to digital converter, kita dapat nilai XN-nya, ya. Nilai XN, ya tentu ada di sini suatu X tanda bintang N karena ada kesalahan kuantisasi, ya. Jadi ada suatu kesalahan kuantisasi, ya kita dekati dengan X pangkat pakai topi N ini. Kemudian kita olah, ya, kita dapat outputnya, kita olah, kita dapat outputnya dalam N, kemudian kita kembalikan ke bentuk melalui konverter digital to analog, ya. Baru kita lewatkan filter rekonstruksi untuk mendapatkan kembali sinyal kontinunya, kurang lebih lah blok, ya. Sample and hold itu, ya, kalau digambar dicuplik, di hold, dicuplik, di hold, dicuplik, di hold, nah, sample and hold, ya. Tentu dia memiliki nilai error, ya, antara nilai yang tercuplik dengan nilai yang sebenarnya, error kuantisasi, ya. Jadi X pangkat pakai topi N ini karena ada nilai error kuantisasi dari XN, ya. XN nilai sebenarnya dengan X pakai topi N, ya, akibat kuantisasi, kesalahan kuantisasi. Jika kita menginginkan 8 level, maka kita butuhkan 3, ya. 8 level kita 3 butuh bit. Kalau kita menginginkan 16 level, maka kita membutuhkan 4 bit, 2 pangkat 4, ya, untuk kuantisasinya. Oke. Contoh soal. X1T 1,5 kosinus 2000 VT dan X2 2,5 kosinus 14.000 T akan dimasukkan ke ADC dengan frekuensi sampling 8000. X1N masukkan T dengan NT. Sinyal manakah dari X1N, X2N yang akan mengalami aliasing ketika direkonstruksi? Berapa frekuensi sampling minimum agar sinyal mengalami aliasing pada jawaban B? Dengan frekuensi sampling pada C, tentukan persamaan sinyal tersebut. Ya. Kita masukkan T ganti dengan NT. Maka kita dapat persamaannya 1,5 kosinus pi per 4N untuk X1, ya. Kita masukkan untuk X2, ya, 7 pi per 4N. Nah, maka kalau kita lihat di sini, sinyal yang mengalami aliasing itu adalah omega 0-nya lebih besar dari V, ya, karena omega itu bergeser dari minus V ke V. Ya, omega 0-nya lebih besar dari V, ya, maka dia mengalami aliasing karena X2. Nah, supaya tidak mengalami aliasing, maka frekuensinya harus, ya, 14.000 Hz. Kalau dimasukkan 14.000, maka dia tidak akan mengalami aliasing.
Recall that in the previous video we had shown that if I have a continuous time signal x of t and I sample it to produce a discrete time signal x of n, then I can associate a Fourier transform with the discrete time signal x of n, and the Fourier transform of the discrete time, or the sampled signal now, is given by 1 over t times the sum from k equals minus infinity to infinity of shifted versions of the original signal Fourier transform. And the amount that these versions are shifted by is omega sub s, which is 2 pi over t, and that's the sampling frequency. In terms of hertz, we would talk about the sampling frequency as being 1 over 2 t. Well, in this lecture, we're going to talk a little bit about reconstructing the continuous time signal from its samples. We're also going to talk about the sampling theorem, which specifies how fast we need to sample a signal to do the reconstruction. So to start, we're going to take a canonical sort of example, one that I can draw, and that is to assume that x of t is a band-limited signal. Now, what we mean by band-limited is that it has no energy above a certain frequency. So if I sketch a spectrum, say x of omega, then the example we're going to do is the famous triangle spectrum. And so we'll have this corner be at b and minus b, and band limited means that x of omega is equal to 0 for magnitude of omega greater than b. Now we're going to consider several cases, and I'm going to start with omega sub s being greater than 2b. In that case, if I sketch the spectrum of the sampled signal, the Fourier transform of the sampled signal, we'll call this xs of omega. Recall that we have replicates of the original spectrum shifted to be centered on multiples of the sampling frequency. So I have one at the origin, and that's the k equals 0 term in our sum, and this amplitude is now 1 over t. And I'm going to have another replicate at omega sub s, and this is omega s minus b. This is omega s plus b. So this was the k equals 1 term, and then I'm going to have a k equals 2 term at 2 omega sub s, and so on. Well, if we talk about the problem of reconstruction, which really amounts to getting x of t back from x of n, that's equivalent to getting x of omega from xs of omega. So if you look at this expression, or this picture here for xs of omega, is there a way that we can extract x of omega from this picture? And the answer is yes. If I simply multiply xs of omega by hr of omega, and we'll make that function to be t, because we have to account for the 1 over t. So we're going to make that t, and it's going to have a value t from out to frequency omega s over 2. So remember, in this case, omega s over 2 is greater than b, minus omega s over 2. And if I multiply these two things in the frequency domain, I will get back my signal Fourier transform that I started with. So that's a simple way to reconstruct. Now this multiplication by this function can be viewed as really what amounts to low-pass filtering, because we're passing the low-frequency components of xs and we're attenuating the high-frequency components. Well, it's useful to look at this operation in the time domain. Recall that what we've shown is that x of omega can be recovered by taking xs of omega and multiplying it by hr of omega. And if I convert that to the time domain, that says that x of t should be given by well, here we have multiplication in frequency, so that's going to be convolution in time. And the continuous time representation for x of n is the sum n equals minus infinity to infinity of x of n delta of t minus nt. So that's my Fourier transform of xs of omega. I have to convolve that with hr of t. We have a simple convolution here. There's a sum of a bunch of terms, but each of these terms, remember, you can convolve the terms one by one and then add them up at the end because the convolution is a linear operation. So if I convolve the impulse with hr, what that does is shift hr to the location at which the impulse occurs, which is at time nt. So we get that x of t is a sum n equals minus infinity to infinity x of n hr of t minus nt. And it's fairly simple to show that hr of t is given by t times the sine of omega sub s over 2 times t divided by pi times t. And this, if we substitute this into our expression for x of t, we get that x of t can be expressed in terms of the samples x of n, sum n equals minus infinity to infinity, x of n, and then we'll have sine of omega s over 2 times t minus nt divided by pi times t minus nt. So hr of t in this case is just a sinc function, and what this says is that we're adding up shifted sinc functions. They're shifted by multiples of the sampling interval, and their amplitudes are scaled by the samples x of n. This is called ideal band-limited interpolation. We can sketch this. So what we have is that for each sample x of n, we have a sinc function that's centered at nt. So this is value x of 0. It's centered at 0, and you see the sinc function here. And that sinc function has 0 crossings at multiples of t. So at where the other samples occur, at time t, at 2t, and so on, all these sinc functions have 0 crossings, and the amplitude is defined entirely by the sample x of n. So exactly reconstructs those amplitudes, and what happens in between is these sinc functions add up in a way shown by my red curve here. These sinc functions add up in a way to produce a smooth curve or a smooth signal going through those points, and that makes sense because we've said that the signal was band limited, which means it can't have arbitrarily fast frequency fluctuations, and the sinc function, the smoothness of the sinc function, is limiting the rate at which the signal can change in the time domain, and that smoothness is defined by the bandwidth that we're dealing with when we sample. The reason this is called ideal band-limited interpolation is because the low-pass filters that we're using to do the interpolation are ideal. That is, they have perfect unity response, and then they go to 0 instantaneously and stay there forever. Or in the time domain, as shown in this expression here, we've got these sinc functions which have infinite duration. So at any point in time, I not only have an infinite number of samples contributing to my signal, but each of these sinc functions goes infinitely forward and infinitely back, making this a non-causal process. So this is not a practical strategy for interpolation, but we'll talk about one of those later on in a future lecture. Well, let's now consider another case for the sampling frequency. Suppose that the sampling frequency, omega sub s, is equal to twice the bandwidth of our signal. In that case, we can sketch, and what happens is that the x sub s of omega, what happens is that the shifted replicates begin to touch. So this is b, this is omega sub s, but that's also 2b. This will be 4b, with 2 omega sub s, and of course this is 3b, and so on, and again we're scaled by 1 over t. So as we decrease the sampling frequency, remember the first case, it was that omega sub s was greater than 2b. Now they're equal to 2b, And these shifted replicates, which I'm labeling here according to their index in the sum, these shifted replicates begin to touch. Different situation entirely when omega sub s is less than 2b. Because in that case, what happens is these shifted replicates start to overlap. So recall the expression says that we add up all these shifted replicates. So in these regions of overlap, we end up, in this case, with a sum that is quite different than the spectrum that we started with. Now, because these are triangles, I can easily add them, although drawing them is always a challenge. You can see that in these regions here between omega s minus b and omega and b, that we have overlap, and the two things add up to give us a quite different value of the spectrum. Well, because of this overlap in these shifted replicates, we can't uniquely recover x of t from x of n. The problem that arises here is that in this region of the spectrum, we have a sum of two things. We know what the sum is, but we don't know what the individual components are. So if I tell you the sum of two numbers is equal to 3, you can't uniquely tell me what the two numbers are. You can give me a lot of possibilities, but you can't give me a unique solution. And that's basically what's happening here. There's no way to separate this where these overlap and to pull it apart into its individual terms. Now this is called aliasing because frequency components in the shifted replicate, and I've just written down here x of omega minus omega s, it shows up in the overlapping with the higher frequencies of x of omega. In other words, it shows up in the wrong place. So we call that aliasing. So this leads us to the sampling theorem, also sometimes called the Nyquist theorem. And the sampling theorem says that if x of t is band limited with zero energy above frequency b, then x of t is uniquely determined by its samples x of n equals x of nt, provided that the sampling frequency, omega s, which is 2 pi over t, exceeds twice the bandwidth. We have some terms here. The frequency, omega equals b, is called the Nyquist frequency, and the frequency omega equals 2b is called the Nyquist rate, because that's the minimum rate at which we can sample a signal and still satisfy the sampling theorem.